Okay, this is the last video on rational functions I'm going to put up today. This is going to talk about oblique or slant asymptotes, and your particular book is using the term oblique. I'm kind of used to calling them slants. I'll try not to do that too much, but they're interchangeable as far as we're concerned here. These are going to occur when the exponent in the numerator is higher than the denominator by just 1. So when I say exponent, I'm talking about the lead term on top, lead term on the bottom. If that difference is just 1, with the highest one being on top, it's going to be a slant. Now the problem is they're kind of hard to see when they're written like, say, this one here. If that would have been a 3, where the 2 is, I could go, oh, okay, so there's a slant, but finding it can be kind of a pain. And I'm going to do some simpler examples first. So here's a rational function that I've kind of simplified a little bit. 3x plus 5 plus 2 over x. And what I like about this one is we can kind of compare it to another function of just y equals 3x plus 5. So I have these two competing functions. Y equals 3x plus 5 plus 2 over x. I have that in yellow for a reason. And then just y equals 3x plus 5. So this one's definitely an equation of a line. This one is a rational function, so it will have a vertical asymptote at 0, has some stuff going on. But what happens to this yellow term as x goes to infinity? So as x goes to infinity, this yellow term is going to get extremely small, and it's going to basically go to 0. So when I'm looking at this function and I'm looking at that function, they only differ by this yellow term. So when the yellow term is basically going to 0, these two functions are going to be hard to tell apart. They're going to be approximations for each other. That function right here, y equals 3x plus 5, would be an oblique asymptote for this one, because as x gets large, this function will approach that line. You notice this is a line with a non-zero slope. It's not a vertical line. It's just an oblique or slant because I have a slope here that's not 0 or undefined. So when I look at that, the point of all this is as I get more complicated functions, here's where I have therefore y equals 3x plus 5 is oblique, I could use this one to estimate this uglier one. I don't particularly have a lot of interest of throwing numbers into 2 over x and adding this all together. I could very quickly do this one. So that's the rationale. As these functions get nasty, we can hopefully approximate them with just a linear equation. Here's another example. A couple more here. Y equals negative 5x plus 2 plus 7 over a monstrosity. But as x goes to infinity, this whole term is going to go to 0. And I'm basically left with y equals negative 5x plus 2. These two will act the same for large x. So instead of talking about this whole ugly rational function, I could just have this nice little linear function. That's an oblique asymptote. This function, when x is large, and when I say x is large, x is going to infinity. It could just as easily go to negative infinity. It's going to approach this asymptote. And for large x, it's not going to cross it. It's just going to approach it. Here's another one. Y equals this. Now, it's written in a different form because, unfortunately, you're going to have to simplify these things. So when they're written in this format, I like to break them up into 3 fractions and then simplify each one of those fractions. Pause this if you need to and look at what I get for my simplification. I'm right back to something that looks like that. As x goes to infinity, 7 over x is going to go to 0. This rational function will approach this line, which is your slant or oblique asymptote. See, I used oblique and here I use slant. They mean the same thing. Now for a tougher one, and you can see what's happening here, I have x minus 3 on the bottom. So I could break it up into 3 like I did up here, but I still have this over x minus 3. It's harder to think about. You're going to have to do long division. You're going to take that and divide it by this in long division. And if you want to take the time right now and try that, you're going to come up with this being equal to 7x minus 10 plus a negative 13 over x minus 3. So I've changed it back to the form like we had before by doing long division. As x goes to infinity, this term is going to go to 0, and the line will approach y equals 7x minus 10, an oblique asymptote. And again, the point of these is to help approximate the rational function for large x. Do you really want to be throwing in, say, 1050? If I want to approximate this for x equals 1050, you want to put them in for all those x's and multiply and divide and all that? Or do you just want to go 7 times 1050 minus 10? Okay, a lot quicker. It's used for approximations. All right, this is the last video on this particular topic.